So in this tutorial, we'll see how to reconstruct or build the missing regions or the missing residues in a PDB file that's downloaded from the protein data bank by using the builder feature in PyMol. That's this guy out here. So usually the missing residues or the missing regions are short fragments that are missing from the PDB file basically, so they could not be resolved by the extracrystallography method for various reasons. Maybe the resolution wasn't good enough, or the process was very cumbersome, or for that matter, these regions didn't form a structure at all. So if these are very flexible regions, as you have seen previously from temperature factors, that some of these regions appear to be very high in temperature factor, which means they are very, very flexible in nature. In that regard, they could not be resolved by extracrystallography, especially. Maybe through NMR methods, they might be resolved to a certain extent. Well, not resolved, let's call it not resolved, but let's say it could be obtained as a loop region. Let's say the NMR structure would show it as a loop region. But in general, via extracrystallography, you can't really predict these missing regions if they don't appear to be very, very structured in nature. So they appear as loops or turn regions, let's say, if they appear between two definite structure forming regions. And mostly these regions occupy the extreme end of the N terminal, that's the starting of a protein structure or a peptide, or the end of the C terminal, that's the end of the protein structure of a peptide. So in our case here, we'll look at the PDB with the ID 1ETH, which is basically the pancreatic lipase colipase complex. So the first thing that we do is we fetch the PDB structure, as you've seen previously in the other tutorial, that we can fetch the biological assembly. That's a CIF file, the CIF file that we can obtain. So by typing the command fetch 1ETH and then pressing enter, will give you the full PDB structure here. So as you can see, there are two subunits. So each of the subunit again is a heterodimer of lipase and colipase. So we don't need all of them. We just need one of the subunits. So we'll get rid of the other subunit in a minute. But first of all, as I have told you before, the CIF files are very interesting in the sense that, when you fetch the PDB in the form of a CIF file, then you'll find that the specific residues or the specific regions constituting residues which are missing will be annotated automatically, as we have seen before with the other structure. So in order to activate that, we have to go to the display and then show the sequence here. So once we show the sequence, we see all the chain annotations here. And as I said, that we need only just one of the subunits. Let's say this subunit, the left subunit, which is subunit 1, and we get rid of the other subunit. So one subunit here is the biological assembly. So let's go through the sequence first. So you see for chain A, which is basically the lipase of subunit 1, you see there are no missing residues because there's no region or chunk of residues that are annotated in gray. These all are in green, which means it only shows the activated region that's being displayed on here in the display of PyMol. But as we go down further in the sequence, we see that for chain B, the starting of chain B, which is the colipase of the same subunit, is having the first three residues missing. So these residues are, well, starting from residue position 1 belongs to the N terminal. So that's valine, proline, and aspartic acid. The first three residues, they're missing in the colipase. And if we go further down, so colipase is a short chain actually. And then from 91 onwards until 95, 95th residue, you see all these residues are missing out here as well, which are all shown in gray. So all the residues that are missing will be shown in gray in the sequence, and we can always reconstruct or model these residues by using the PyMol builder function here, which we'll see in a minute. Let's traverse through the sequence a little bit more. So as we go down further, we see that chain C, which is basically lipase of another subunit, is having none of the residues missing here, just like chain A. And chain D, which is colipase of another subunit, is having the same residues that were missing for chain B as well. And if you go down further, we find chain E, chain F. So these are all the ligands that we used in the structural characterization. And then you have some calcium ions as well. So you can annotate these calcium ions. We'll get rid of all of these because what we are concerned about is modeling the protein part only. So in order to get rid of all the chains, but just retain the colipase, which is the chain of our concern, because this is the fragment that is having all the missing residues here in the N terminal and the C terminal. We'll just get rid of all the other chains. We'll remove all the other chains and just retain chain B. So in order to do that, just go to the command line interface of PyMol and do a selection. Let's say select cell. So cell is the group in which all the residues will be stored for the selection. So select cell, comma, and then chain C. So we'll first delete chains C to F, and then we'll go ahead and delete chain A because chain B is lying in the middle. So if you do chain A to F, then it will delete everything. So chain C and then colon F. So it will select all the chains and all the residues and atoms corresponding to chains between C and F. So C, D, E, F. Enter. So you see all the selections made, and this is pertaining mostly to this subunit, the other subunit. And then we'll type in the command remove SEL. So you see all the chains C to F are deleted from the other subunit. Okay. Now we'll delete chain A, which is the lipase of this subunit. We do a selection for chain A now, which is select cell chain A. So you see all of the chain A is selected. In the sequence, you can see it being highlighted, whereas in here, it's not being highlighted for some reason. Doesn't matter, as long as you can see that the selection is made, and it will always be displayed on this terminal that the selection has been defined with this many number of atoms, which in this case for lipase of one subunit is 4,800 atoms. So we'll remove again, remove cell. Okay, so that selection is removed now, and then we end up with only the colipase and some water molecules. Okay, so we're basically going to delete all the water molecules now. So we do another selection, select cell RESNHOH, which stands for the three-letter code, residue code for the water molecules, and you see all the water molecules being selected. Now, as I've told you before, the water molecules does not have a one-letter code, so they are all being represented as 0, but you can identify them easily in a PDB file when you open that up in PyMol. So remove cell again, that is removing all the water molecules, and the water molecules are gone. So we end up with only the colipase of the first subunit, which is basically chain B. Now we are going to model the N-terminal missing residues and the C-terminal missing residues. So extreme start of the structure and the end of the structures. But before we use the builder tool out here to reconstruct these residue regions, we'll basically annotate the N and the C terminal, that is the existing N and the C terminal, which is proline in the N terminal and valine in the C terminal, in a more acceptable representation, let's say a licorice representation. So the reason being, the carbon of the carbonyl group carbon of the valine will form a bond, a peptide bond or an amide bond with that of the nitrogen of the glycine out here, and the nitrogen of the proline will basically form a peptide bond with the carbonyl carbon of the aspartic acid out here. So once we have a licorice representation, we can specifically annotate those atoms that will be responsible for forming the amide bond or the peptide bond. Okay, so let's go ahead and do the selection. Without typing in here, we can do the selection right away from the sequence menu out here, which is select for the proline, and you see the selection has been made for the proline, which is the N terminal, and then the valine, which is the C terminal out here. We'll just rotate the structure a little bit so that it's easier for you to appreciate. So now we have the N terminal on the left and the C terminal on the right. And once we have done this selection, so it's stored in the select group here. So we'll go to S and show this as a licorice on top of the cartoon representation that we already have. So once we show that as licorice, and you can see the licorice representation being shown out here, and we'll color this a little bit differently, let's say by element, and let's say we select the third option out here. So you see it's of a different color and a different representation altogether. So once we are happy with it, we'll go ahead and start the builder tool out here. So you go to the right in this panel and click on the builder tool. It will ask you, so building undo is disabled for the following objects. So we don't want to disable the undo, so we want to enable it. So basically press yes, and we see the builder tool appearing. Once you drag along the builder tool and bring it on to the right, it will be stuck on this panel on the right here, which is very handy. We can operate from here directly. So a builder tool is a very efficient function where you have all those fragments which you can add onto the structure wherever you need it, as well as the protein residues which you can add and the nucleic acid residues which you can add. So we're basically concerned about the amino acid residues which belongs to the proteins. So we'll go to the proteins panel and you see the 3-letter codes of all the residues, the protein residues being represented out here. Okay. Now, what do we want these structure formations to be? So you have 3 options for the secondary structure. One is the alpha helix, the other one is the beta sheet, and the third one is the second one is the beta sheet antiparallel, and the third one is the beta sheet parallel. So if you select alpha helix, then it will basically create a helical kind of secondary structure for these regions that we will build on top of the existing N and C terminals. We don't want that. So a beta sheet is a more acceptable format because you don't have a format for a loop region out here. They don't give you the option for reconstructing it as a loop region. So the safe bet out here would be the beta sheet in the anti-parallel orientation. So select this. And now we got to annotate the specific atoms on top of which we will be building all these residues. So let's go to the N terminal first. So if you want to focus on this particular residue, which is proline out here, as you can see with the 5-membered ring that's being annotated, and we click on the middle mouse button. So once you click on the middle mouse button, this brings into focus the proline residue in the N terminal. And then we drag along by clicking on the right mouse button in order to zoom into the structure. And you can clearly see now. So another thing that you will find once you activate the builder tool out here, you'll find that automatically the mouse mode is changed to 3-button editing as opposed to 3-button viewing, which means you can actually select the atoms and the bonds associated with the specific residues, the amino acid residues. So as I said before, since this is the N terminal, we'll build on top of the nitrogen atom out here. So we click on the nitrogen and you see a selection is made for the nitrogen. And on top of this, we are going to build on the aspartic acid, which is the next residue, starting from right to left in the N terminal, basically. So the aspartic acid 3-letter code is ASP, and once you click on it, you'll find that automatically the aspartic acid residue forms a peptide bond with that of the nitrogen of the proline residue that's adjacent to it in the next in the sequence, basically. And on top of that, Builder also makes an automatic selection for the next nitrogen, which is the aspartic acid nitrogen, which will now form a peptide bond with the carbonyl carbon of proline, which is next in sequence out here. So we'll basically click on proline, which is 3-letter code of PRO. So we click on proline, we see that the proline residue is built on top of the aspartic acid. And then the next one that you have is valine, because the nitrogen for the proline is already selected out here. So this is a fascinating thing with the builder tool, that it automatically recognizes in which terminal do you want to build on the residues, the missing residues basically, and it keeps on selecting the respective atoms, whether be it the N terminal, the nitrogen for the N terminal, or the carbon for the C terminal. So the last residue that's missing out here, and starting from the N terminal, is the valine. So we select VAL from here. And there you go. So all the 3 residues that we're missing in the N terminal is being built now. Now, the structure is not represented in the licorice representation properly. So we'll just zoom out of this and make a selection of the first 3 residues that we just built. And you see all the gray regions have disappeared and they have been replaced by the green regions, which means the structure, or let's say the loop region, has been formed in here. So once we do a selection of the first three residues that we just built, we are going to go to the selection again and show it as licorice representation. And now you see both the cartoon format and the licorice format are being represented properly. So you see this loop region has been built. Okay, so we are done with the N terminal. The N terminal missing residues have been built. Now we go over to the C terminal. So we drag along by clicking on the middle mouse button and just zoom into, bring this residue in the middle. So the C terminal residue, which is valine, is brought in the middle, and we drag along with the right mouse button and so that it zooms into this particular residue. And now we got to make a selection for the C terminal carbonyl group, which is basically the carbon atom out here. So we are already in the 3-button editing mode. And once we click on this, so we see this is the carbonyl group and the carboxylic group, basically, which is represented by C double bond O. And once we select this atom, which is the carbon group corresponding to the carboxylic acid, and we are going to build on top of this. So this is the valine residue that we have, and next to that there's this glycine residue, and arginine, serine, aspartic acid, and serine. So we are going to first build the glycine residue. So once we click on glycine, it makes an automatic reconstruction of the glycine residue, and immediately the gray region is changed to green, and it makes a subsequent selection of the carbon atom, the carbonyl carbon or the carboxylic carbon on the glycine residue now, which will be bonded to the nitrogen of the arginine. So the next residue in the chain is the arginine in the C terminal. So we click on ARG, and the arginine residue is reconstructed on top of the glycine, and it makes a selection of the carbon of the arginine residue, which will now be bonded to the nitrogen of the serine residue. So we build on serine residue on top of the arginine residue, click on serine, you see the building is automatically done. So next in sequence is the aspartic acid. So ASP, it's this guy out here. And finally, it's ending the C terminal with serine residue. That's the 95th residue. So you see the carbon atom of the carboxylic acid group of the aspartic acid has been selected, which will now form a bond with the nitrogen of the serine residue. So select serine out here, and you see all of these gray regions have been turned into green, which means the missing region in the C terminal has been built now. That's great. So I'm just going to represent this last 5 residues again as licorice so that all the atoms and the bonds are represented properly. Go to show and then show it as licorice, and you see all of these are represented properly. And if you see the structure as a whole, find that the N and the C terminal are being reconstructed as loop region. So that's great. Okay, now we're going to save the structure. So we have this new PDB file. We're going to save the structure as sport molecule. We create a new atom order because we have reconstructed the residues. We go to PDB options, but we retain the atom IDs and write the header information for each object, which is very handy for reading. And then we save it. So once we do a save, I'm already inside the workspace tool. I'm going to give it a name as 1ETH underscore mod and just change the format to PDB and just put the extension as 1ETH underscore mod. So it's a modified 1ETH file that we have out here. Save, and the save is done. Okay, so let's close this and open the newly saved structure that we have. So go back to the terminal and just I'm going to type in PyMol 1ETH underscore mod PDB, and you see it's just having the colipase chain of the first subunit with the N and the C terminal loop regions reconstructed or rebuilt. That's great. Just to cross check, we are going to go ahead and display the sequence. And you find here, so valine, proline, and aspartic acid on the N terminal, and starting from residue number 91, that's glycine, arginine, serine, aspartic acid, and serine in the C terminal. These are the residues that are built separately as loops. Now, although we have built these regions as loops, it might not necessarily mean that they are in the favorable energetic position, which means they need to be comfortable out there and be as close as possible to the native structure, getting favorable, or let's say a global minima kind of structure. So in order to do that, we'll have to refine these loop regions. That is, have them in a conformation, not form a structure with it, but have them in a conformation where it is most comfortable around the other residues and there's not much of a steric hindrance. Well, just by looking at the structure, you can see that they are kind of far apart from the other loop regions or the other structure formed regions. But we just want to be sure. We just want to be as perfect as possible. So we'll do a loop refinement. Now, the loop refinement could be done by using the feature of modeling, which is also another program which does some homology modeling. And we select these loop regions separately in the modeler interface, and we ask it to refine the loop regions to pose it in its most energetically favorable conformation. Now, modeler comes as a standalone program, as well as you can have it from the web interface as well. So they have a separate web interface, which is for modeling loop regions. It's called ModLoop. So if you search for ModLoop in Google, it will bring you to the first search hit, which is ModLoop Modbase. Click on that, and it'll take you to the page where it says ModLoop, modeling of loops and protein structures, and it will ask you for your email ID. So you'll always have to have the university email ID. That's the UL ID that's there. So I have mine here, and the modeler license key. So modeler license key is universal. Well, they ask you to obtain the license key, but you can always have this key in here, which is universal and it applies to all and everyone. So it basically reads as MODELIRANJ. And so the next thing that it asks is upload the coordinate file, which is the newly saved PDB file that we have with the reconstructed loop regions. So we choose the file, just go to my workspace, so workspace 2. That's the name of the file, which is 1eth_mod.pdb that we newly wrote, just there. We open it, and now they ask you to select the loop segments, that is the regions that you want to refine, which in our case are the N and the C terminal regions. So 3 residues in the N terminal and 5 residues in the C terminal. So the way we annotate is, so you already know that the co-lipase here is belonging to chain B. So we give the number corresponding to the residues, which is the residue number or the residue ID. So starting from 1 in the N terminal, followed by a colon, and the respective chain ID, which is chain B, followed by another colon, and then the end of the loop region that we reconstructed in the N terminal, which is residue number 3, followed by the chain ID, and then you end with another colon out here. So these are the N terminal loop region residues that we reconstructed, and we want to refine them. Next, we press enter, and in a separate line, we have the C terminal residues, which are basically from 91 to 95 in the chain B. So 95 colon B, then further colon 95 B, ending with a colon. Okay. So you can name your model. Well, this I have as autosave, but you can name your model as, let's say, 1ETH or something, and you can name it anything. It's just a job annotation name that you need to have in order to, process or get the results later on easily. Okay. And once we click on process out here, so it'll take you to a new page where it says your job has been submitted to the server. Your job ID is 1ETH, which is what we gave, and the results will be found in this link, and you'll be notified. So you'll get a separate notification on your email ID as well. when the results are available and the job finishes. So you can check on your job in the modeling queue status page, which we'll see in a minute. And the following loop segments will be optimized. So that's what we gave for the loop regions that we reconstructed. And then you have estimated execution times, 90 minutes. Well, these are short loop regions. This won't take that long, but it might take a while, let's say a few minutes at least. So let's check the job in queue. So once we click on this link, let's open it in a new tab. So ModLoop queue status page. And if we click on this, we'll find that the job key is 180H or the job ID, and the time of submission of the job is given out here, and the status of the job is running. So if you click on show, it will show all the description of the different status. So incoming is basically the job is successfully submitted, but not even started running. Queued is basically there are other jobs in queue as well. And running is what we have out here. So the job is running at present. Once it's completed, show the status is completed. And if it fails for some reason, let's say there's a technical fault or any other reason due to, let's say it cannot really refine those loop regions due to excessive static hindrance or close contacts between residues, then it will notify you as failed. Okay. So after waiting for a while, let's say if you receive, you will receive an email notification with the job finishes. And now we'll go back to the results tab that we have opened already. So ModLoop results, click on it and just refresh the page. So on top of the email notification, once you receive it, just go ahead here and refresh the page. And you'll find that the job has been completed. So job name was 180H has been completed, and it gives you an option to download the output PDB file. So there's an additional option to download the modeler script. So as I told you before, that modeler is a standalone program as well that's compatible with Windows machines and Mac machines and Linux machines as well. And it runs basically on a Python-based scripting language, and they have separate scripts for all the functions that we need to perform. So for this particular case, it's the remodeling of the loop region or refinement of the loop region. That's a separate script for that, which you can run on your machine as well by running a Python script basically in a way. And so the job results will be available for 6 days. So we go ahead and download the output PDB. That's the newly refined loop region for the N terminal and the C terminal that we constructed. So we save it in the workspace 2 directory, and let's say we give it a name of 1ETH and loop refined.pdb. Okay. So we save it here, and now we want to open the newly written PDB structure with the loop refinement. So we go back to our workspace and we open it with Chimera, let's say. So 180H loop refined.pdb. And you see here, the loops have been refined. So if you want to see what refinement it has done on the loop, so we'll do a superimposition of the previous structure that we had written already. So if you hover over this residue, you'll find that this is the C terminal, and this is the N terminal basically. So that's 95, and that's residue number 1. And we switch this over. And we are going to open again the previously written PDB file without the loop refinement, that is with just the reconstructed loop regions. So we go to File and Open, and we go to that specific workspace 2 directory, and we open this previously written PDB file, which is 180h mod.pdb. So once we open that, we'll find that the two structures are superimposed on top of each other with exactly the loop regions showing the differences, whereas the other regions are exactly aligned with each other. So it didn't change anything else in the structure. It just refined this loop region. So the ones in the red are the previously built loop region or reconstructed loop region, whereas the ones in the blue color are basically the newly refined loop regions that you have. So that's great. You have a refined loop region, and we reconstructed the loop region at first, and that's how you generate the missing residues of a PDB file in a short fragment. So the missing residues necessarily, if you want to reconstruct them by PyMol, it has to be less than 10 residues.